Swayam Prabha. Digital India. Educated India.
We will continue our discussion on one-dimensional Euler equation in this lecture. So, in the last lecture, before concluding, we had talked about the one-dimensional Euler equation in their vector form, and if you recall, we talked about two vectors, the vector u, which is concerned with the conserved quantities, conservation of mass, momentum and energy, and the flux vector f, which comprised of the different fluxes, the different flux quantities. So, if you look at the components of the u vector, you find density rho as the first component, then the product of density and the velocity. Here it is a one dimensional problem. So, there will be only one component of velocity, namely u, and then you have the product of density and internal energy in its total form. And in the flux vector f, the first component is again density times velocity, the second component is density times velocity square plus pressure, and the third component is a summation of density times total internal energy plus pressure, the whole multiplied by the u component of velocity. So, these are the different components. We are talking about vector conservation law. So, we are no longer having one equation to handle, but multiple equations to handle here, and we therefore represent them in a more compact form in the vector form. So, this is the compact representation of the one dimensional Euler equation. So, just to look at the familiar forms once again, if we look at the continuity equation, then it is the time derivatives of density plus d dx or rather del x of rho u equal to 0. The momentum equation so, as we mentioned earlier that we are going to prefer the conservative form of equations because they are inherently more suitable to handle flow fields with discontinuities like shocks and contact discontinuities, and Euler equations are capable of capturing such discontinuities. So, we would like to have them in the conservative form where we handle fluxes, and though there could be discontinuities in certain derivatives like say velocity derivative across such discontinuities, but the fluxes will not jump. And coming to the energy equation, so these are the familiar partial differential equations that we are aware of to represent the conservation of mass, momentum and energy. So, when we look at the flux vector form, it is a very compact representation of the same. So, coming back to the flux vector f, we are talking about the different components in terms of mass flux, momentum flux, in addition to the pressure force which is involved through the pressure gradient term in the momentum equation, and the third component is the total energy flux plus pressure work. So, these comprise the different components of the flux vector. So, we may very often in vectorial form represent this vector u by its components u1, u2, u3, and the flux vector in terms of its three components f1, f2 and f3. Step at this point would be to represent the different components of the flux vector in terms of the different components of the conserved quantities. So, let us try to look at that aspect gradually. So, before we do that, we would like to mention that sometimes the flux vector is split up, because you have seen that the second and third components of the flux vector comprise of two terms, not a single term. And very often we would prefer to segregate out the pressure contribution from the regular fluxes. So, in that case you would write the flux in the form of summation of two separate vectors, one with only the influence of the velocity field, the other only with the influence of the pressure field. Of course, here as far as energy equation is concerned, there is also a velocity field involved, but it is primarily based on the pressure or the other part that we segregate this. And then a very important part that we can look at in terms of information about how the equation behaves actually comes from the non-conservative form, where we define the Jacobian matrix A. So, in order to define the Jacobian matrix, we start from the conservative form of the equation, the left hand side of the conservative form of the equation, and then we split the spatial derivative. So, we split it into two portions, one is df du, and then we multiply it with del u del x, and we call this as the Jacobian matrix. Now, remember that both f and u are vectors. So, when you take a derivative of this form which involves vectors, you would come up with matrices, because there are multiple components contributed from both ends which lead to a matrix formation. That is why what we come up with is a matrix here, a matrix A, which we would call as the Jacobian matrix. And a lot is interpreted about the nature of the equations from this Jacobian matrix. We will see soon, and that is why we take this non-conservative form to come up with the Jacobian matrix and try to utilize it to extract more information about the equation. So, when we look at the Jacobian matrix, we see different components of this kind. So, remember that you are taking a derivative of f with respect to u. So, if you look at the first row of the matrix, you find that the first component of the f vector figures here. So, derivatives of that component with respect to the different components of u, they will form the elements of the first row of the Jacobian matrix. Of course, they are all partial derivatives, right. So, this makes it obvious that we would like to have the functional dependence of f1 on u1, u2 and u3. Only then can you evaluate these derivatives. If you go to the second row of the Jacobian matrix, you can similarly see that the partial derivatives of f2 come in over there with respect to the three components of the u vector, and similarly the third row involves f3. So, these are the three rows involving partial derivatives of the different components of the conserved quantities. All right. So, the next step, the next obvious rational step that we need to take is try to express f1, f2, f3 all of them in terms of u1, u2, u3. Only then can we obtain the different elements of this Jacobian matrix, right. And then the normal course of action which you are aware of even from earlier modules where we have discussed about partial differential equations, that we try to extract eigenvalues of such a matrix in order to understand the behavior of the system of equations. So, that comes later. So, let us try to do this activity of representing the different components of the f vector in terms of the components of the u vector. So, let us see how we go about doing it. So, if you just keep the two vectors in front of you, you can clearly compare that f1, which is rho times u, is nothing but u2 directly. It does not have any dependency on u1 or u3, but it directly equates with u2. How to find out f2? f2 is by definition rho u square plus p. Now, we can obtain rho u square rather easily, because u2 is rho u and u1 is rho. So, if you take a ratio of that, you will get rho u square. So, it is u2 square by u1, but we do not know how to go about with pressure. So, for that we do a simple calculation which we have shown here on the right side. So, we first define the total internal energy in terms of its static and the dynamic part, and then we realize that we can actually express the static part in terms of say two thermodynamic variables like pressure and density. So, this is a form of the equation of state itself, where E is equal to P by gamma minus 1 into rho. So, if you have this relation, then that helps us, because we can then go ahead and write an equation for pressure which is equal to E rho times gamma minus 1. Keeping gamma minus 1 outside the bracket, we replace the E by E t and u square, half u square inside the bracket, and then multiply it with density. And then you see conveniently that the first term is nothing but u3, and the second term, just like what you did over here, can be easily represented in terms of u2 square by u1. So, pressure now is expressed in terms of u1, u2 and u3. You have the functional relationship. So, that is plugged in over here, and then you can actually come up with the final expression. So, we were looking at the second equation. We will go back to this. So, it is plugged in over here, and then we club the terms together. So, you now have the functional dependence of F2 on U1, U2 and U3, right. So, having said that, we go to the F3 part now, and then using very similar approach we try to proceed. So, rho E t plus P the whole into U. So, we have already obtained an expression for pressure in terms of U1, U2, U3. So, that functional dependence has been worked out already, it is convenient for us, and then we already know that rho E t is nothing but U3, right. So, this is known to you, and so is your pressure, and therefore, if you just put in those steps together, you will find that the function f3 can now be expressed using this equation in terms of u1, u2 and u3. So, we tried to work this out and we have achieved this goal. We have found out the relationships, and now in order to fill up the different components of the matrix A, we have to actually work out the derivatives, right. So, in order to work out the derivatives, you have to work out terms like say del f1, del u1, del f1, del u2, del F1, del U3 and so on, right. So, in order to do that, you take the expression for F1 for example, and if you take a derivative like this, then because it is only dependent on U2, this will become 0, this will be 1, this will again be 0. So, that fills the first row of the A matrix. If you go to the second row, then you have to work with this expression and then take the partial derivatives with respect to U1 first, then U2, then U3, right. So, if you take with respect to U1, then you will find the different components and you can do the simple calculations. So, you can say del F2 del U1. So, that will be 3 minus gamma by 2 and then it will be U2 square into minus 1 by U1 square, and once you collect them together. So, it is we will put it as gamma minus 3 by 2 and then if you gather those terms together, it turns out to be U square, because U2 by U1, if you take a ratio, it will give you U and then it is squared. So, that gives you del F2 del U1, del F2 del U2 will give you so, that is what it will give you. Then going to del F2 del U3, that will give you gamma minus 1. Now, we can just complete it by doing the del F3 del U1, which is the third row of the Jacobian matrix. So, you will see it is gamma U2 U3 into minus of 1 by U square minus half gamma minus 1 U2 cube into minus 2 U1 to the power of minus 3. So, let us collect the terms. So, this is what the expression will be. So, we have filled all the different components of the Jacobian matrix in this manner. There are of course, alternative ways also to express these terms, where we bring in say enthalpy. So, we have actually done this step already We have just shown an example once again of one of those partial derivatives. As I was telling you earlier that there are alternative forms of this equation, this should be T, and the one that we have obtained is essentially this, but there are alternative forms where you can have the total enthalpy coming in. So, in your spare time you can try exploring the alternative forms. As you can see that up to the second row of the Jacobian matrix there is no difference, it is only in the energy equation that you see the difference. So, that is the third row of the matrix, which is essentially the third component of F, where the difference is. Now, in the previous lectures, you will recall that we have relooked at the scalar conservation equations related to the wave kind of problems. So, we looked at some of the results specifically for linear advection equation and Invisit-Burgers equation. So, they were all scalar conservation laws. Now, once we get into one dimensional Euler equation, even with one dimension we have a vector model, because we have continuity equation, one component of momentum equation and energy equation, which are a combined system of conservation laws which have to be handled. Therefore, it becomes a vector model problem. Now, when we talk about waves or wave kind of solutions for vector model problems, we represent the system in this form, where as you can see that U is now a vector. The coefficient matrix is no longer a single parameter. If you recall that in linear advection equation or wave equation, this was A. So, it was just a constant, or in Invisit-Burgers equation it was U, the velocity component itself. But now, we have a matrix here, because we have a vector model in place, and we now know it is the Jacobian matrix, and A essentially is a square matrix. We have three conservation equations here. So, A is a 3 by 3 matrix. Now, this system of equations is going to be hyperbolic in nature, that means with wave kind of solutions only if this matrix A is diagonalizable. So, we come up with a new word, diagonalizable, and we try to understand what that means. So, we write down an equation over here involving the matrix A, and we bring in another matrix Q, which is essentially derived from the matrix A itself. But it is not only Q that is involved in this equation, but it is also its inverse. So, the left hand side of this equation we can see it is a product of three matrices, Q inverse, A and Q, and remember that this matrix Q or Q inverse, they are derived from the matrix A itself. Now, this product that you have on the left hand side of this matrix equation will ultimately give you a diagonalized or diagonal matrix on the right hand side. That means, the right hand side matrix will only have non-zero entries in its diagonals. All the non-diagonal elements will be 0. So, if this equation is derivable, only then will this system of equations be hyperbolic. So, if this equation is possible to derive, then we say that the matrix A is diagonalizable. So, let us look at a little more details on the matrix Q or Q inverse. So, as we already mentioned that the right hand side diagonal matrix has only non-zero diagonal entries, and these diagonal elements are lambda i's or characteristic values or eigenvalues of A. So, sometime back we were talking about extracting eigenvalues of the matrix A, because that tells us more about the behavior of equations. So, we now find that these eigenvalues of A are available directly in the diagonal matrix capital lambda, and all these diagonal elements can be represented by the small lambdas, in general represented as small lambda I. Now, coming to the matrix Q and Q inverse. So, Q is a matrix whose columns are right characteristic vectors or right eigenvectors of the matrix A, and Q inverse is a matrix whose rows are left characteristic vectors or left eigenvectors of matrix A. So, this is how Q and Q inverse are defined. So, once you define matrix Q, Q inverse in terms of A, and you are able to come up with this equation, then you can say that the system is hyperbolic. Now, having said that, we will look at one step more, where we multiply the above system of equations which we have on top by Q inverse. So, Q inverse is the matrix which comprises of the left eigenvectors of A, we remember that. So, we are multiplying the vector model equation by Q inverse. So, this is the first term, this is the second term. Now, we are proceeding towards forming the characteristic form of equations. So, that means we are converting the equations from the plane of conserved variables u to another plane, where we will talk about some derived variables which are the characteristic variables, and we call these characteristic variables as v. So, there is going to be a vector comprised of characteristic variables, say having the components v 1, v 2, v 3, like you have u 1, u 2, u 3. So, how are the characteristic variables defined? They are defined using this equation. So, dv is q inverse du, okay, which also means that du is q dv. So, keeping this in mind, we are going to look at the full form of the characteristic equation. So, you have it here. So, you have dv dt, then the product of these three matrices times dv dx, or rather del v del x, even this was del v del t, is equal to 0, and you recall that this product should give you the diagonal matrix capital lambda. So, now what do you have? You have the system of partial differential equations represented in the characteristic variable space. So, earlier it was in the space of conserved variables, while now you have written down the equation in the characteristic variable space. So, we will finish this lecture here. We will continue our discussion on Euler equations in the next lecture. Thank you.